I'm Frank Chiou,
I'm Danny Solivan.
and we're a group of 14, and we worked on the USB arbitrary waveform generator.
First off, we'll start with what is a waveform generator.
So, a waveform generator is a device that outputs waveforms in the form of voltage. It does this by adjusting the voltage level over time. So this is a waveform generator. Usually they have presets that you can adjust. So you can adjust it to like square wave, triangle wave, or various other things. So this is a sine wave. We'll just stick with that. So the usage of a waveform generator is to test circuits, and this allows us to do that by controlling the input, which allows us to meaningfully analyze the outputs.
These waveform generators that we have at OSU's lab are relatively expensive and typically cost over $1,000. Our goal was to develop a USB-powered arbitrary waveform generator that is inexpensive because this is a product that will be potentially given to freshman ECE majors to own and use. The first design requirement we had was that the device should be affordable. To be affordable, we set the requirement as under $100. Our second requirement was that it would use a CSV file to save waveforms and be used for importing custom waveforms. Our third requirement was that it use a GUI to control the operation of the device. Our fourth requirement was that it be powered entirely by USB. Our fifth requirement was that it be intuitive to use. By intuitive, we mean that it should be easy to set up, the program should be easy to use, and have a very low learning curve. Our sixth requirement was that it be, quote, freshman ready. And by freshman ready, we mean that it should be durable because freshmen are commonly not careful with their things. Freshmen may also plug things in improperly, and the device must withstand power surges and being shorted. The device should also be portable to carry around and utilize BNC connectors because these are standard issue for freshmen. And finally, the device must also utilize a PCB to be easily replicated. One of our unique design choices was that we didn't use a microcontroller, but only a FIFO chip. We chose the FTDI FT2223HL FIFO because it could directly communicate to the PC via USB. For our device, we used the FIFO in synchronous bit bank mode. This means that when new data arrives at the FIFO, the value that was already stored inside the FIFO's queue will be output. With this, we were able to control the output frequency by controlling how often we sent new data to the FIFO. All of this control was done through the GUI interface that we developed. Next, we'll go into our block diagram.
So this is our top level block diagram. I'm going to start with the power block. The power block takes in 5 volts and up to 500 milliamps from USB. It outputs 5 volts, negative 5 volts, and 2.5 volts. Next block is the Visual Basic GUI. It takes in config data. This is the configuration data to control what kind of wave you want. This is set in the user interface. It allows the user to select the type of wave and set parameters for the wave. The Visual Basic GUI block exchanges control data with the VB. This allows the GUI and the FIFO chip to communicate with each other. The USB FIFO chip block takes in 5 volts. This is used to create 3.3 volts to power the chip. The FIFO chip takes the control data from the GUI and translates it into a parallel 8-bit data stream and sends that to the DAC. The digital to analog converter block takes in 5 volts and 2.5 volts. The 2.5 volts is used as reference, and the 5 volts powers the DAC. The DAC takes in data sent from the FIFO and translates it into a small voltage, and this is sent to be amplified in the output amplifier block. The output amplifier block takes in 5 volts, 2.5 volts, and negative 5 volts. Like in the DAC block, the 2.5 is just a reference voltage. The 5 and -5 is used as a range for the output amplifiers. This allows the output to be from -5 to 5 volts. The output amplifier block amplifies the voltage received from the DAC and outputs the desired wave. The enclosure block is just the case for the device. It's built to withstand impact or crushing force. All blocks on the VB GUI receive a environmental input, which means they must be able to withstand normal environmental conditions, defined as 0 to 120 degrees Fahrenheit and dry conditions.
Now on to our project demonstration.
Alright, so this is our hardware demo. So it's pretty easy to set up. So this is our BNC connector. We need it to be freshman ready. So here's a BNC cable. So all you have to do is just hook it on. And these two ends go to the circuit that you're going to be attaching this to. Not too hard. Positive side, ground, okay. So this is a oscilloscope probe. Goes to the oscilloscope, so we can measure what's coming out. Yeah. And this end is USB. It's a USB arbitrary waveform generator, so you know, standard A, standard B. And this end goes to the computer. So the hardware really doesn't work right now, so that's why the oscilloscope isn't outputting anything. So I guess that's it for our demo.
This is the software demo portion of our demonstration. First off, our software was coded in VisualBasic.net, and the IDE that we used was Microsoft Visual Studio 2010. We chose VisualBasic.net because it was easy to create an intuitive interface for the users of a waveform generator. Now onto the GUI. The GUI uses push buttons to the right here to create preset types of waveforms, similar to the Tektronix waveform generators that we have in lab. The presets here are sine, sawtooth, square, and triangle waves. These are pretty standard among waveform generators. The settings for these presets can be tweaked down here. Here we can set the amplitude, frequency, duty cycle, and DC offset. When a waveform is generated from a preset or from loading a CSV file, an array is created with the corresponding 8-bit digital values, which will be sent to the FIFO. In addition to these presets, the program also supports the loading of CSV files for your arbitrary waveforms. Here I have a sample CSV file that has an update frequency on how often to update each symbol in Hertz, and my waveform with voltages ranging from -4 volts to 4 volts. Now I'll have the program import the data values into an array for output. Now onto the mechanics of the program. The program uses the FTDI D2XX drivers, which allows direct access to the USB FIFO via a dynamic link library. The DLL file provides functions for us to connect to the FIFO and write data to it. Using these functions, we are able to send out continuous data to the FIFO at 12 megabaud. With this rate, we are capable of making our goal of 10 megasymbols per second, but only with USB 2.0. And for our last section, here are some helpful hints for future seniors. First off, you want to make sure that everyone in your group has a fairly diverse personal background in ECE classes. Like before, we used to have tracks, so you would ideally want someone maybe like in computers and networking, another in integrated circuits, and another one in power.
Yeah, so when we were working on this thing, we realized really quickly that we were all computer networks, so we all had a lot of programming background, but not a lot of anything else. And so we just sort of wung it for constructing like the power block and stuff. But, you know, it might be a good idea to diversify.
Also, another thing is that you should order extras of everything you get. This may put you over your budget, but it's better than, oh no, our single part failed. We have to wait 3 days to
get one single part.
Yep.
Yeah. Or, you know, you might have to pay overnight shipping, and that's terrible.
And that is the end of our senior project video. It's been a great experience for us, and thank you for watching.